welcome to week 4 live session of molecular spectroscopy, a physical chemist perspective. Today we are going to solve a few numerical problems, and let us start with that. We are going to solve some numerical problems from the rotational and vibrational spectroscopy. Some problems that we could not solve the last session, and I have noted some other problems from online, various universities lecture videos and lecture notes from. I have collected a few questions. We'll try to solve a few of them today and maybe on next session. um, so let us start with that. We will start with week 3 assignment solutions. This solution is already given to you, and we'll just try to quickly solve this question and then we'll go to the numerical problems. So let's start. The first question says the spacing between the successive energy levels of a harmonic oscillator is what? So we remember that the harmonic, if it is a harmonic oscillator, then the potential energy curve looks something like this, right? A parabola, and where this is your x, which is direction of vibration, or you can say coordinate of vibration, and this was your energy, and your this looks like a parabola, right? So v is equal to potential is equal to half kx square. That's why it turns out to, and these are your vibrational levels: 0, 1, 2, 3. These are your v values. So as you can see, the spacing is always the delta E is always delta EV is always going to be h mu vibration of your molecule. So this is your actually the spacing is going to be same for all. Okay. Now the next question. The next question is the correct statement about both the average value of position and momentum uh, p of a 1D harmonic oscillator wave function is what? So if you remember the quantum mechanics, how to solve that question and how to solve the Schrodinger equation and all, you will get to know that actually the average value of position and average momentum. So position and not the momentum, but the average values are actually can be zero. Okay, so individually, not so. So the average value of x can be zero, average value of p can be zero. Okay, so the third option is correct. Now, question number 3, wave function of a harmonic oscillator are. So, you may argue, so actually, wave function is going to be real. This is the correct answer. But the thing is that you may argue that it has a exponential term, whatever that, but it is not only exponential, it has a Hermite polynomial to it, right? So, it's not really a exponential, but it's a, so the safe answer would be a real wave function. Question number 4 is the vibrational frequency and anharmonicity constants are given of an alkyl halide. That is, the vibrational frequency is given at 300 centimeter inverse, and anharmonicity constant, that is Xc, is given as 0.0025 respectively. So we need to calculate the position of the fundamental mode. So let us remember. So when the for an anharmonic oscillator, remember that what is uh, the expression for energy? It is something like v plus half. V is the quantum number. Here I am. So instead of, so you can, so right now I am writing it as a wave number. Okay, so that I can have the unit of centimeter inverse. So don't be confused with that. Half square pi. Now this is the uh, your, I should write this as the unit will be in centimeter inverse. If I would have used to get it in a joule, I have to write it in this way. So you have to be confident with this. Um, uh, uh, what should I say? Um, this unit to business. Okay, so you need to be very mindful about this. So the unit will be here in joules, right? Now let's put the values maybe. So given that your yeah, for a so you see you remember what is a fundamental transition? Fundamental transition is 0 to 1, V 0 to 1. Okay, so this is your V double dash, this is your V single dash. So this is ground state, this is excited state. So you need to have your energy values, right? What will be E0? It will be XC. This is in centimeter inverse. And what about your E1? This is right. So now the fundamental mode transition will be a gap between that. So or you can also see. So now the gap will be delta E, right? So that will be E1 minus E0 would be E minus 2. So this in centimeter inverse. So this value is given. No, not this value is given. You need to have calculate this value. This VE that is given. This is your VE, that is the vibrational frequency, and this is your XC. This is given. So let us see what is your coming as delta epsilon for fundamental. It will be 300 minus 2 into 300 into 0.0025 and centimeter inverse, right? So it will be less than 300 but not very less, right? Something like we are going to get actually 98.5 centimeter inverse for this. Actually, this is the correct answer. Okay. Now the next question, that selection rule for harmonic oscillator arise from. So recursion formula of the Hermite polynomials. This is obviously the correct answer, one of the correct answer. What about the next recursion formula of Legendre polynomials? See, Legendre polynomials is not required here, right? Legendre polynomials comes in, you may say, the rotational spectroscopy, not here. What about the third point? Requirement of a non-zero transition moment integral. See, here it is a non-zero transition moment integral. So it should, your transition moment integral should be non-zero, right? For a allowed transition, so it is the correct answer. If it is saying that requirement of a non-zero dipole moment, then I should not take this as a right answer because mu can be zero. The main funda was that your mu or dipole moment should change during the vibration. But so dipole moment, the non-zero dipole moment is not required at the starting. Okay. Now what about the fourth one? The spacing between the successive level of the oscillator. That doesn't really matter, right? So, the selection rule depends on these two factors. Okay, now let us see the question number 6. The question number 6 says that the 0 point energy of a vibration 35 Cl2 mimicking a harmonic oscillator with a force constant K 2293.8 Newton per meter is. So see, here you want to calculate 0 point energy. You remember what was the 0 point energy? 0 point energy was so energy of the V is equal to zero state. What is the formula for when no harmonic means anharmonicity is not there for a harmonic oscillator? It was V plus half H nu, right? In joules. So so a 0 point energy ZPE is 0 plus half, right, is 6.626 into 10 to the power minus 34 joules second. So this is your H, Planck constant. Into your, you will record the value of nu. Nu is what? Is vibrational frequency. How, and your, but your, that is not given, but the molecule is given and your force constant is given. So if you remember what is the relationship between your nu and these things, that so let me write, nu is your vibrational frequency, it is related to the force constant by this formula, right? 2 pi root over force constant by your reduced mass. So what is the reduced mass? Your molecule is given for 35 Cl2. So you know what you have to do, 35 into 35 by 70, actually 35 AMU, atomic mass unit, or Dalton. Okay, so this is actually 35 by 2 into 1 point. Now I will take it in kgs. Okay, 1 AMU is that much kilogram. So I will put this value here and let us see. Is 1 by 2 into 3.14, and K is, force constant is given 2293.8 Newton meter inverse divided by actually 17.5 into 1.66 into 10 to the power minus 27 kg. Actually the Newton meter inverse is kg. What is Newton? Kg meter square second minus 2 meter inverse. So this kg meter, okay. Am I making any mistake? Yes, it should be Newton meter. So it will not be here. So the value of, So as you can see, the it can be written as kilogram second inverse, second minus 2, right? So we'll just change, maybe in this color I'll write this, that we can write it that also, kg minus 2, right? So I'm writing this unit so that you get a better idea, right? So I will calculate this value and let you know. So 1 by 2 into 3.14 into root 2293.8 divided by 17.5 divided by 1.65 divided by 10 to the power minus 27. So it is coming as 4.47. So I have already put the root value also, 4.475 into 10 to the power 13 second minus 1, that is in Harj. That is also Harj. Uh, Now I will put this value here, right? 4.475 into 10 to the power 13 second inverse. Now see, second inverse, second cut, and you are going to get some value in joules, right? So I'll calculate that also. 6.626 into 10 to the power minus 34. I am getting a value of 1.48 into 10 to the power minus 20 joules. See, there is no minus 10 to the power 20, so, and the close is, so I will just multiply it by 10 and divided it by 10, right? 14.8 into 10 to the power minus 21 joules. You see, so this is your correct answer. So it's all about playing with the units. Now question number 7. So the vibrational energy levels V double dash is equal to 0 and V double dash is equal to 1 of a diatomic molecule are separated by 2143 centimeter inverse. Its anharmonicity WE into XE is 14 centimeter inverse. The values of WE in centimeter inverse and the fast overtone in centimeter inverse we need to calculate. So I will use a different color to distinguish between this question and this one. So I will start from here. So as we don't have much space, see, uh, 0 to 1, the vibrational energy level gap is given by this. So this is actually your, um, you can say, this is your fundamental, because it is 0 to 1, right? So did we calculate it earlier? What is going to the fundamental? See, we have calculated here. So this is actually, if I take common VE, so 1 minus 2 XC centimeter inverse. This is given 2143 centimeter inverse is given, is actually your VE 1 minus 2 XC. Okay. Now your, we need to calculate what is your VE, that is your actually vibrational equilibrium vibrational frequency. I will erase this bracket. I am expanding this, minus 2 VE XE, and this value is given, right? 2 into 14 centimeter inverse. So from here you can calculate what is going to be your 2143 plus 28 centimeter inverse. So this is going to give you 2171 centimeter inverse. So only this option is correct, what I can see, 2171, right? And also let us calculate the fast overtone. What is going to be the fast overtone? So fast overtone you will require your E0. E0 is, we have calculated earlier also. So E0 is half so you need to remember a few questions for this. Right? If you so for fast overtone you need E2. E0 to 1 was transition was fundamental. Now 0 to 2 is fast overtone. This is actually going to be 2 plus half, which is 5 by 2 V minus 25 by 4. So your fast overtone is going to be gap between this E2 minus E0, which is actually your 5 minus 1 by 2, which is 2V minus 25 minus 1 by 4, 6V XC. And this is, if you, I won't take this common because I already know these values. V1 2171 minus 6 into 14 is coming in centimeter inverse unit. So this is 2 4 3 4 minus 84 8 9 5 2 4 4 to 5 8 centimeter inverse. So here this is correct answer. Okay, now let me switch back to this pen. Maybe I will like this. Now the spacing between the successive energy levels of a anharmonic oscillator. Now it's not a harmonic oscillator anymore, and the potential will follow Morse potential. It will look something like this. And actually, if this is your first gap, actually your successive energies are going to decrease with increase in energy, and ultimately you are going to get a dissociation energy here. It's not maybe I will need use another from 0 From 0 it is known as dissociation energy, and from 0 point energy it is known as D0. Okay, we'll need this in upcoming numerical problem. So let us go to solve some more numerical problems. This was the last question for week 3 assignment. Okay, so let us calculate the ratio of n1 by n0 both of the molecules in V is equal to 1 and V is equal to 0 vibrational state for the carbon monoxide at 25 degrees Celsius. Assume a harmonic oscillator with a uh, vibrational frequency 2169.8. Hint, at 25 degrees centigrade, your KBT or KT is 207.2 centimeter inverse. So we are going to solve this question by two way, the calculation actually. But let's see what we are going to arrive at. So, so this is a question of population, right? So for vibrational energy levels, uh, the population is dependent on what? So we will follow actually the Boltzmann distribution, right? But what about the degeneration? So for each vibrational levels, how many? So each vibrational, suppose for V1, how many degenerate states are there? You are going to see the degeneracy is only one for vibrational spectroscopy. Okay, so let us do that. Then what is going to happen that n1 by n0 is actually going to depend on the energies or the Boltzmann constant. So minus energy of the state E1 by KT, right? And below this is going to be minus E0 by KT. What is E1 or EV in this case? EV we know V plus half H nu in joules, V plus half nu bar, not that is in centimeter inverse. See, these are all going to give in centimeter inverse, so we are going to use that. Let us write nu E. So what about energy of E0? That is VE by 2 centimeter inverse. What about E1? VE 3 by 2 centimeter inverse. So if we simplify this, we are going to get E0 minus E1 by KT. So let us do that. So we are going to get VE by 2 minus 3 VE by 2 by KT. See, uh, exponential minus 2 VE by 2, it is going to be VE, right, by KT. Now KT is given already in centimeter inverse, so we'll just put the values. So your VE is also given 2169.8 centimeter inverse divided by 207.2 centimeter inverse. So this is actually going to be exponential minus. So I will calculate this and let you know. 9.8 divided by, this is coming as 10.9.472. what is going to be the value? Exponential of is going to be 2.832 into 10 to the power minus 5. See, the value is very small. Okay, so if so, so at room temperature, you can see that almost no molecules are there in the uh, if there is 100 in n0, then it is below 1, means which is actually 0, right? There is no molecule in n1. If there is 10 to the power 5 molecules in n0 or the ground state, the population is 10 to the power 5 molecules, then your n1 there is 2.8, which is almost 3 molecules are there in the n1. So see, for vibrational energy gaps are such that at room temperatures only the ground state is populated. So let me write it down. What are we learning from this? Right? Okay. Now the same condition for the rotational levels. Let's see what is going to happen. Same. So n1 by n0. See now, here comes the degeneracy factor, and then your Boltzmann thing. So what is G? Gi is actually going to be 2I plus 1, or it's better I should write 2J, Gj, jth level, right? 2J plus 1 is going to be the degeneracy. So for the first excited state, the G1, it is going to be 3, right? And for ground state, it is 1. What about the energies? So let us write what is EJ. EJ is B into Bj into J plus 1, right? In centimeter inverse, so I'll multiply it by AC. So to be in the joules, right? Let me be in centimeter inverse, as the unit is eventually be in the centimeter inverse is given, right? So what about E0? E0 is 0. What about E1? E1 is 2b centimeter inverse. So I will put these values. Exponential, actually I will make it short. E0 minus E1 by kt. Let me give this bracket. So it is going to be 3 into exponential 0 minus 2b is going to be 2b divided by kt. Kt is given and 2b, b is given, see, be. So 3 into exponential, this is how much? This is minus 463.8, right? Divided by 207.2 centimeter inverse at the numerator, also in denominator it is centimeter inverse, so it will get cut. Eventually I will give you the answer how much it is going to come. 3 into exponential of minus 3.864 divided by 207.2. It is going to give me 2.945. So see here, for it is showing, even if my at ground state there is one molecule, but in my excited state, fast excited state, rotational excited state, there is three molecules. So see the energy gaps, the population at the higher energy levels can be higher than the ground state. What I am trying to say, that the energy gaps are very less here. So I will write it down here again, like the same way. Energy gap between levels are negligible. So the population at excited state is or are significant, right? And you already know that it will go through a maxima. First, it will increase at certain temperature. It will means the population. So if I draw the curve, it will look something like this. Um, this is rotational energy levels, and suppose this is population this way. So it's going to follow something like this. It will increase up to a certain point and then again it's going to decrease. So it will follow some signature like this. Okay. So it will go through a maxima. And you already know how to calculate the at which j you are going to get highest nj, right? You just need to give take a derivation of this one population, that suppose nj is dependent on gj into exponential minus ej by kbt. You just need to derivatize these ones to get with respect to J to get the value of maximum J. Okay. Next question is the lowest energy transition in the rotational spectrum of HF are 41.105 and 82.211 centimeter inverse. Calculate the equilibrium bond length of HF and R0. So here you see we need to calculate the equilibrium bond length R0. So and it is from rotational spectrum. So you know which equation to use, right? So the equation is the equation of rotational constant. The rotational constant is B is H 8 pi square mu is the radius mass uh, R naught square C. So this is your rotational constant and this is your reduced mass. So it is given it is HF. So let us calculate the reduced mass. So 1 into 19 by 20 AMU, which is 19 into 20 into 1.66 into 10 to the power minus 27 kilograms. Okay. Now we know the unit of okay, I'll write it later. Now if I take R0 square R0, if I need to calculate R0, so I will need to take square of this square root of this 8 pi square mu B into C, right? So I'll expand these values. So 6.626 into 10 to the power minus 34 joule second. So this is 8 into 3.14 square into mu is 19 by 20 into 1.66 into 10 to the power minus 27 kg, right? What about B? See, we don't. Do we have the value of B rotational constant? Yes, we have. See, here it is written the lowest energy, the gap between the lowest energy. So the lowest energy transitions are given. See, this is if we, this is your uh, new bar or wave number, and this is your intensity scale. So they are saying that the first transition occurs at 41.105. The second transition occurs at 82.211, and you already know the gap between the rotational spectrum is going to same, and also it is 2b. The 2b is 82.211 minus 41.105 centimeter inverse. So from there you are going to get your b value as 41.106 by 2 centimeter inverse, which is 3, then 5520.553. Okay, so this in centimeter inverse. So we will put this value here again, right? 20.553 centimeter inverse, and we are still have to write C will write in centimeter second unit. We can remove this joule second to another unit, which is kg meter square second minus 1. So now you can card this second inverse, centimeter inverse centimeter card, kg card. So the unit will come up is meter. And what is the value is coming up? I will quickly write it down here. 9.295 into 10 to the power minus 11 meters, which is in picometer it is 92.95 picometers, or you can also say 0.9295 angstroms. Okay, it depends in what unit they are asking. Okay. Okay, so now let us go to the next question. So the next question is the two adjacent line in the rotational spectrum, again the similar kind of question, is 14N 1H are at 98.036 and 130.714 centimeter inverse. So we need to calculate the equilibrium bond length again of HF, R0 and the rotational quantum numbers of the lower state of the two transitions. See, let us do again the same thing. Let us first calculate the mu, the reduced mass of 14N 1H is 14 by 15 into 1.6 kg, right? Now we know what is going to be 2b, gap between two rotational spectrum, right? 130.714 minus 98.036 centimeter inverse, which is 684,716. Now 203. I have made one mistake, maybe. May not be. Yes, 32 point. So 8203 centimeter inverse. So your B is gap of this, which is 16.339 centimeter inverse. So again we know the equation, which is this, and your R naught 6.626 into 10 to the power minus 34 kg meter square second minus 1, and in denominator it is going to be 8.314 square of that, then 14 by 15 into 1.66 into 10 to the power minus 27 kilograms kg cut, and then your B value is going to be 16.339 centimeter inverse, and then your velocity of light in centimeter. Centimeter inverse gone, second inverse gone. So you are going to get your answers in meter. So let me calculate how much it is. So 6.626 into 10 to the power minus 34 divided by 8 into 3.14 square. coming as 1.052 into 10 to the power minus 10 meter, which is 105.2 picometer, or you can say 1.05 angstrom, right? Now, other than the previous question, matlab, apart from the previous question, here the additional question is find out the rotational numbers of the associated transitions. So let me use a different color maybe for that question. So see, uh, you remember, right? These are the energies of the transition. So what is going to be the, suppose your, so this is your initial stage, and selection rule says delta j is equal to plus minus 1. So let us see if it goes from, the transition is from j dash j double dash 1. So what is going to be the energy difference? So the energy difference is actually, you know the equation, it is 2b into j double dash plus 1 is going to be some energy. So for the first case it is 98.036, right? So you know what is the value of 2b. Now j dash plus 1 is actually your 98.036 divided by 32.678. So what is going to be j dash? So let us calculate this. 98.036 divided by 32.678 minus 1. So it is coming as 2. Okay. So this transition, the fast transition, associated j double dash being 2. Now we'll use a different color for the another one. So similar to be j double dash plus 1 is now 130.714 centimeter inverse. Okay. So what is j double dash here? It is going to be 130.714 by 32.678 minus 1, and it is going to be, let us see, I think it's going to be 3, I guess, but let us calculate once. 130.714, and the other thing, it is actually coming as 1, 3. So actually this is, so the not the fast, I should not write the energy associated energy of 130.714 inverse associated energy of, you should write the unit always, right? With j double dash 2. I hope you will be able to solve this kind of numericals, right? So let us go to the next problem. the next problem says calculate the moment of inertia of water about z-axis, which is the figure axis. The rotational constant about z-axis is given. Here it is given as A. We use that as B sometimes. So A is given 14.512. Assume the bond angle is 104.48 degree. Calculate the OH bond length. See, here we are dealing with moment of inertia. So you remember the equation. So this is has to be do something to do with the rotational spectroscopy and something to do with the rotational constant. Some rotational constant is again given. So I'll first draw the structure. So this is your oxygen. This is your hydrogen. Okay. And suppose it is making an angle of, suppose this is 2 theta. It is given the angle is 104.48 degree. Okay. And also it is given that this is Z. Let me draw the triangle in black. Okay. So what is given? Your A, that rotational constant here, that is given as 14.512 centimeter. I should write, I may write AZ, rotational constant about Z axis. Okay. What AZ is can be related to, again it is related to H by 8 pi square IC into C, the speed of light, right? IC is, this is, and write this in a different color maybe. This is movement of inertia along z axis. So this is the first question we want to have the answer to. So let us see. We have the values as Iz is going to be H by 8 pi square A into C. হ্যাঁ প্রজিত দা, হ্যাঁ হ্যাঁ পড়াচ্ছি আমি। শর্মিষ্ঠা জি, ডেস্কটপ ডেস্কটপ, ঠিক আছে। কি নাম? প্রিয়া বাইরে আছে, প্রিয়াকে ফোন করো, প্রিয়া বা সুচেতা। So we will put the values. So this is coming as Joule. So I'm thinking what, so Let me write the same kg meter square second inverse. This is a better unit to work with so that I can show you how can I cut with cancel with other units, right? This is 14.512 centimeter inverse, and to cut this I need to take my speed of light as 10 to the power 10 centimeter second inverse. Second inverse gone. Centimeter inverse gone. So I'm going to get IZ as 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 14.512 divided by 3 divided by 10 to the power 10. I'm getting a value of 1.929 into 10 to the power minus 47 kg meter square. Okay, now this is my first answer which I wanted. So I still have another question that calculate the OH bond length. But see, so if now let us go back to this triangle. So this angle between HOH is 104.48 degree. Now suppose what are the mass or what are the atoms that is contributing to this moment of inertia along the z axis. So the atoms which are not sitting on the atoms which are sitting on the z axis will not give any contribution. The contribution will be zero. Okay, because the x, the distance is actually zero. Let us take the origin, oxygen as origin. Then you will consider that it is sitting on z, so it will not have any contribution on the uh, rotation moment of inertia along the z. But the hydrogen atoms which are there on the other which are not on the z axis will have contribution each and same. So what will be the contribution uh, if uh, so this is theta, this is theta, and this is one triangle. So only the hydrogen is going to contribute here, and this hydrogen is going to contribute here. So for each hydrogen, what is the contribution? Let us see. So it is going to be so actually your and it is also given that this is in a same plane. Okay, so I will see this as my mh 1 mh, and from this triangle what is this distance? So from this triangle I can see the distance is, if I take sine theta, suppose this distance, so this is going to be mx square if this is the distance, and so this is for one and this is for second hydrogen, so mh1 plus mh same distance but minus x I am taking because, so I can take actually x because the distance is x, so the coordinate can be minus x, but this is for the second one. And as the hydrogen atoms are similar, so I will take this as 2mh x square. So the sine theta is x by this R0, the bond distance ROH. So AX is actually ROH sine theta, and theta is how much? 57.24 degree. Not 57. I 9. It should be. Did I make any mistake? What did I do? Yes, this should be 52. It's my mistake, please. Sorry. This should be 52. So eventually this is the value. So mass of one hydrogen is 1 AMU into 1.66 into 10 to the power minus 27 kilogram, right? And for X we already got ROH sine theta, which is actually sine 52.84, sorry, 24 degrees. Again, square of that is going to be 1.2929 into 10 to the power minus 47 kilogram meter square. So kg and kg will cut. ROH square will be 1.929 into 10 to the power minus 47 meter square by 2 into 1.66, so 10 to the power minus 27, and sine 52.24, we need to get the value of that. Sine 52.24 square of that is 0.625. Okay, now let's see what is going to be my ROH is going to be. Actually, the previous step I can write is going to be square root of all this, and the unit is going to come as meter. So I will take this 1.929 into 10 to the power minus 47 divided by 2 divided by 1.66 divided by 10 to the power minus 27 also divided by 0.625. It's coming as 9.642 into 10 to the power minus 11 meter, or picometer, or you already know 0.9642 angstrom. Okay, now this is your bond length. From this question what we have learned, so for a nonlinear molecule how to work with the moment of inertia and all, right? Okay, now from this question we will go to the next question, and next question is from a vibrational frequency and very easy problem. So that we need to calculate the bond constant kappa or K for H35Cl, which is HCl. Fundamental vibration frequency is given 2990.9 centimeter inverse. From all of this, we remember only one um, equation, that is, if it is frequency V nu E, then it is 2 pi kappa by mu which is reduced mass. If it is given in centimeter inverse, then it will be 1 by 2 pi c. This is the main part where you need to be very careful that with what we are dealing with frequency or wave number. It is written frequency, but from the unit you can say this is in centimeter inverse, so you need to take the appropriate formula. What is the reduced mass for H35Cl is, we will take 1 into 35 by 1 plus 35 mu, which is 35 by 36, and we'll convert it to in kgs. Okay, and from here we can see what is my kappa is going to come as 4 pi square c square mu bar is square into mu. So 4 into 3.14 square into 3 into 10 to the power 10 square centimeter square second minus 2. What about this? 2990.9 square centimeter minus 2, and now mu 35 by 36 into 1.66 into 10 to the power minus 27 kg. And let us calculate the value what we are going to get. 4 into 3.14 square of this into 3 into 10 to the power 10 into 2990.9 square of that into 35 divided by 36 into 1.66 into 10 to the power minus 27. It is giving us 512.44. So this centimeter square, this is 1 kg second minus 2. So this is what we are getting as unit, and this is your uh, force constant. So another unit is also Newton meter. Newton meter inverse. Okay, why? See, Newton is kg meter square, kg meter inverse second minus 2, and if you multiply it with kg, yes, Newton meter inverse. Newton is kg meter second minus 2. Okay, now let us go to another question. This question is, does CH or CO have greater bond strength? Base your answer on the fundamental vibrational frequency for 12CH, which is 286075 centimeter inverse for 12CH, and for 12C and 16O, which is 2169.76 centimeter inverse. See, again, bond vibrational frequency and bond strength is related to bond strength is related to force constant, right? Greater the force constant greater the bond strength. Now you remember the equation, right? Which is 1 by 2 pi c by km 4 pi square c square. Instead of m, I write mu as I was writing everywhere, the reduced mass. Okay. So see, for what is mu for 12 ch? 12 into 1 by 13 amu. What is mu for 12c 16o? 12 into 16 by 28 amu, which is, let it be like that. Suppose the force constant, so I will just take a ratio of um, suppose force constant for 12 ch divided by force constant of 12c and 16 oxygen. Then see, these are common, 4 pi square c square. So this is for 12 ch, and again mu is for 12 ch. Then here it is common, 4 pi square c square mu square is 12c 16 oxygen into reduced mass of 12c 16 oxygen again. So this part is common, so we can cancel it, right? This value is given. So for CH it is 2860.75 square of that centimeter minus 2 into 12 CH is 12 by 13 AMU divided by 2169.76 square centimeter minus 2 into 12 into 16 by 28 AMU. So let me cut the units, cancel the units. 12 also cut. So I am left with 286075.2169.76 square into 28 divided by 13 into 16. So I will cut it further, 447. So this is actually 7 and this is 4. So let us see how much it is coming. Is it coming greater than 1 or less than 1? 2860.75 divided by 2169.76 into 7 divided by 52. It is actually coming as 0.234, which is less than 1, right? So your K12CH, the force constant is less than C16O. See, actually this is a triple bond, right? We know carbon monoxide, and this is single bond. So eventually, by looking at this, we know that triple bond is going to be stronger. But mathematically, we have derived that the force constant of 12CH is eventually going to be smaller than the force constant for this bond 12C16O. That means that 12C triple bond 16O is actually going to be much stronger. So have a greater bond length. So we'll write that CO have the greater bond length. Okay. So now we will discuss this question. Uh, this is going to be a very important question. So we need to determine the equilibrium frequency, vibrational frequency, the force constant, the 0 point energy, bond dissociation energies for 14Na based on a fundamental vibrational frequency that is given nu naught equals to 11.23.4 centimeter inverse, and anharmonicity is also given 9.0 centimeter inverse. Okay, we need to report these bond dissociation energies in centimeter inverse, electron volts, and kilojoule per mole. Before going there, I will I want to discuss that thing that for a harmonic oscillator, this is an approximation, right? So in this case, this is zero. Potential actually follows a perfect parabola, right? So for this case, our 0 point energy is not zero. This is 0, 1, 2, 3. In this case, our energy is given by, for a V plus half h nu, or let me write it in terms of nu bar only. Nu bar centimeter inverse. Okay. So what is the 0 point energy here? 2. Now when anharmonicity comes into the picture, then actually it follows, the potential actually follows Morse potential curve. Now this is same 0 and this is x. Now this is your 0 point energy, but as a consequence of anharmonicity, actually here with increasing vibrational frequency, here this into, and at this point, this, after this energy, if it goes to this vibrational state, the bond is going to break. So this is known as dissociation, and this is known as D0. Okay. So the energy for this kind of system for a vibrational level is actually is changes a bit, right? V plus half. So let me write this as new 0 and this as equilibrium minus V plus half Xc. And for next vibrational level it is, so I missed the square here, sorry for that, Xc, right? Okay. What about here? So what is the gap for this case is this. Okay. And for this case, the gap is this, actually we can write actually V plus 1 by 2 plus 1 okay. So this is nothing but what I am trying to do. Okay. So in this case it is am I doing the correct thing? Okay. So this is where I have made a mistake. It should be minus, right? So what are we going to get from here? The minus 1 square b plus half square x. This you can cut. So you are here with 2b plus 2 vxe. So if you take this as common, you have 1 minus 2 common b plus 1 x. Okay. See. So and eventually you are going to see that the gaps between when the anharmonicity is being introduced, the successive gaps between the vibrational states are going to decrease. But let us, for the fast 0 to 1 transition, for 0 to 1 transition, the gap is will be almost equal, right? So from that approximation, suppose we are taking this as equation 1 and this as equation 2, So suppose delta E when V is actually 0, then it is also this is this, and then if V equals to 100 is 0, it is going to be mu E 1 minus 2 hc. So this is your equation 2, and this is equation 1. Then from 1 and equation 2 can actually write, so you can write this, right? If I expand it a little bit, so you may have wondered why did I solve, why I am doing this for this question. So now you will get the idea. See, for this question, your fundamental vibrational frequency is given, which is V naught, right? Again, fundamental is from 0 to 1, right? 0 to 1 transition, that is given, which is your 1123.4 centimeter inverse, that is here, and your anharmonicity is also given 9 centimeter inverse, and you need to calculate your VE, equilibrium fundamental vibrational frequency. So now I will change my color. Equilibrium fundamental equilibrium fundamental vibration frequency, which is mu E, is equals to VE HC, which is now 1123.4 plus 2 into 9 centimeter inverse, so which is actually going to be 11, 11, 18, 18 plus 2, 3 is going to be 41.4 centimeter inverse. So this is one of the, so this is the first of the lot. Now what next? Now you need to calculate force constant. Let us do that. Again, we already know what is our force constant going to be from this equation, that 1 by 2 pi c k by mu. So your k is going to be 4 pi square c square mu. What is your mu here? 14 nf. 14 into 19 divided by 33 AMU. 14 into 19 by 33 into 1.66 into 10 to the power minus 27 kilograms. So we put the values here, 4 into 3.14 square into 3 into 10 to the power n square centimeter square to, what did we get, 1141.4, 1141.4 square centimeter inverse, right? Inverse and square of that, then we are going to deal with square. by 2 into your mu, 14 into 19 by 33 into 1.66 into 10 to the power minus 27 kg. Okay, actually these and these will cut. So let's see what value we are going to get. 4 into 3.14 square into 9 into 10 to the power 20 into 1141.4 square of that into 14 into 19 divided by 33, 1.66 into 10 to the power minus 27. So this is giving us 618.75 kg. Acha, I have missed this unit also for minus 2. So this is the force constant. So we can also, so this is the second part. So what was required to solve this question was just to get the idea what is the relationship between your mu 0 bar and mu e bar, right? Okay, now we have to calculate 0 point energy. So what is 0 point energy here? So 0 point energy ZPE is going to be 0 plus half mu bar minus 0 plus half square mu bar xc. VE is already known, 11.41.4 by 2 centimeter inverse minus 1141. Acha, this is 9 is given, no? So I will not write this. So this is given 9 by 4 centimeter inverse. So let me calculate. 1141.4 divided by 2 minus 9 divided by 4, that is 568.45 centimeter inverse. Okay, so this is your 0 point energy. Next what? Next we need to calculate bond dissociation energies. Okay, DE and D0. So see, I have plotted the DE is the gap between this and this, and D0 is the gap between DE and minus ZD. So you can say your relationship between here is DE here is D0 plus 0 point energy. Okay, we will use it, but there is another formula we are going to use, that is the relationship between anharmonicity and your dissociation energy. So your DE I square by 4 BEXE. So dissociation energy eleven four 1.4 centimeter minus 2 square of this 4 into 9 centimeter minus 1. So we are going to get 11 for 36,188.7 centimeter inverse. So we need to calculate this in EV also. But before EV, let me go to joules. So to go to joules, I need to multiply this thing with actually AC. Okay, this is in centimeter inverse. Remember, from joule, when for rotational constant from joule to centimeter inverse, we divided it by AC. So to get back to the joule from centimeter inverse, we need to multiply with AC. We will see what we are going to get. H is 6.626 into 10 to the power minus 27 joule second, and here 3 into 10 to the power 10 centimeter second inverse. Second inverse, second gone, centimeter inverse, centimeter gone. So we are going to get this thing in joules. 36,118.7 into 6.626 into 10 to the power minus 27 into 3 into 10 to the power 10. So this is we are going to get in joules, but 7.194 into 10 to the power minus 12 joules. In other way, we can write it as 7.194 into 10 to the power minus 15 kilojoules. But this is for one molecule of 14 NF. So to get per mole inverse, we need to multiply it with Avogadro number. So now the unit become kilojoule per mole inverse, right? Two seven kilojoule mole inverse. Okay. So this is the dissociation energy in centimeter inverse and kilojoule per mole inverse. This is another part we wanted to know. So I'll highlight it here maybe. So this is one of the highlights, right? Then we have calculated T0 as 36,188 centimeter inverse. This is one, and also 433.27 kilojoule mole inverse. What about, so this is actually E, and what about D0? D0 is 36,188.7 minus the 0 point energy, right? Which is 35,620.25 centimeter inverse. Okay. And centimeter inverse, and again, if we need to go to joules, then we need to multiply this into with Okay, I have done one mistake here. See? Okay, I will. So this is actually 34. Then how did I got the right answer? Let me check it out once. Maybe while using the calculator, I have put the right values. 97 okay. No, I have not done that. So this is a proper mistake. 9, then this should have been 22, 19, 6.023 into 10 to the power 23, which is, my god, I made some errors in uh, maybe in power. I have missed some power earlier. Uh, yeah, and this is then I will go back to, so this 35620.25 into 6.626 into 10 to the power minus 34. So you need to be very careful with this. H into 3 into 10 to the power 10, which is giving me 7 point, maybe 7.08 into 10 to the power minus 19 joules, and divided by 10 to the power 3 kilojoules, and then I need to multiply 3. So it will be 426.46 kilojoule mole inverse. Okay, I did not calculate in the EV also, right? So actually 1 joule is actually 6.24. 6 point. I am making some mistake. 1 joule is actually one, an electron volt. It is what I remember. It is 6.24 24 into 10 to the power 18. 18. I think I am correct. So I need to multiply the joule factor only. So I will just multiply that. So that is 7.194 into 10 to the power minus 19 divided by multiply by 6.24 into 10 to the power 18. actually 4.49 electron volt. Same here also we can calculate 7.08 4.41 42 actually to be precise PV. So I will mark these answers. Okay, so these are the values are required, but as the time is not there much, so we will stop it here today. And I actually had a few more numerical problems, so what we can solve maybe on the next days. uh, okay, so with this we will stop here and we'll meet on the next Tuesday and we'll solve some numerical question. Thank you for joining. Hope this was a helpful sessions for you.